This episode is all about FEM. It's episode 4 of our MTB Frame Development video series. We are pretty exhausted. We are in week 5. We're just running and operating a regular business here. It is crazy. We are getting tired and we are really looking forward for 2 weeks of Christmas holidays. So what happens today? We're gonna show you the FEM results and how they alter our design decisions. Of course, we don't just want to make fancy pictures and we don't have the ability to do proper FEM or FEA analysis in-house. So we partnered with our Australian distributor, Alex Wallis, and he had a really good presentation what FEM is and what it's used for and how to apply a mesh. And then afterwards, Luca will walk you through the design changes. In the end, I will have a nice video from the actual first CNC operations on our head tube. So we give the word to Alex Wallis right now.
For finite element modeling, or FEA, finite element analysis, is the ability to analyze the structure. Now, in its simplest form, these are elements. Each of the parts, this whole thing would be, you could treat it as one element, which would be the top tube, one element, which would be the down tube, one element, which would be, and you could join it up as like a set of triangles. You can do a calculation, and that's what you do when you do hand calculations. And when you first start doing work as a student, you'll do it that way around to do the calculation. So you could do a very simple finite element, which is just beam model, and you'll get pretty good results. You will be able to see that you've got high shear and bending moments in different areas. Now, with the computer powers we have nowadays, we can not just do something like that. We can actually refine that so much that we can create very detailed meshes with very high number of these little elements, and each of these elements we solve a calculation on. And the finite element means you take this little line and you do the calculation on that line. How much does it deflect under how much load? And you keep doing this calculation every time you have an element. And now in a 3D model, these elements are going into the material, around the material. You can sort of see around where we've got areas of high information. We have very small meshes here. So each of those is a little solution. And then here we have, like, for example, we have a tube where we don't need much information on the surface, but through the material thickness, we need to have a lot of information. So we have lots of elements through the thickness. And in this case, being a composite tube, we have lots through the layers. Mm-hmm. So there's mesh refining inside here where the glue starts. There's a whole refined mesh on the inside of that one. And so the calculation does that. And it solves every single one of those lines. If you measure this in the 3 dimensions, solving these equations. So a solution for something like this calculation, you can only do this on the computer, because to do this by hand would take many people many thousands of years. Yeah. and nowadays on a computer, this one here for this type of mesh is running around about 3.5 hours, 4 hours. On this very high resolution mesh, which we've got a couple runs on, we've got results in the background. They are running around about 6-hour calculations, and we're talking these are double CPU computers with 2 processors and lots of memory. We do this inside the CAD programs. We can bring it straight into something like SolidWorks simulation, and we also use another thing called Abacus, a simulator, to do these calculations. And the output from these, obviously, is we work out every bit of deflection. We call strain, and strain becomes known as a stress, which is the pressure in the material. That tells you how hard the structure is working, and all materials have a limit to the point where they will no longer take any more load, and then they'll start no longer being like a spring. They'll start plastically deforming, and hence they get to a point where they deform and break. And yeah, this is what these finite element calculations are all about. They allow us to do very complex calculations in a matter of hours, which would have taken us a matter of years. 30 years ago, this would have been a fairly long calculation. Mm-hmm. Right, and as we saw in the discussions later, the outputs are all these things called stresses and displacements, and we have things called strain, which we look at for all the characteristics. But we can model lots of details. We can model different materials all in one go. So this is called an assembly analysis because it's got multiple parts in here. You can do single part analysis. Yeah, I think that explains roughly what FEA is.
So thanks to Alex Wallis, now everybody should have a good understanding what FEM is. And now we want to walk you through our lug design and explain you in detail what we figured, what we learned from the FEM simulations, how we implement it into our design moving forward. We actually use the EFBE load cases as we go testing with EFBE, and we use them from the category 5 on downhill level. And the first load case scenario is either you have a case landing where basically the fork gets stretched forward, or you have a wall impact where the fork moves backwards, and this implies a lot of stress into the head tube.
Here we have high stress in this area, so we can just solve this problem by adding more material at the gusset area and also have like bigger ratios to have a better stress distribution.
And as simple as this can already lead to a much better result and a much longer fatigue life. Okay, so what was the next load case? It was a one-sided pedal load, right?
Yeah. Yes, so in this load case we apply a force in one crank of the bike. One lug was approaching its limits. So I'm talking about the seat tube bottom bracket lug. So as you can see here we are red. So it means that we reach the limit we defined for the material.
And then we made the adjustments in the part. Maybe you can show the part.
Yeah, sure. So to solve this problem, we simply add more material in this area in order to reduce the stress.
Okay, and this was a static load case, and there's also a dynamic load case, but the results from the dynamic load case were basically suggesting the same changes, so we didn't have to make any other changes. And we found another little weak point or stress riser in the design that we could eliminate with the FEM.
Yeah, sure. I will just talk about it with the next load case, which was the jump load case. We simulate the case of a hard jump landing. So when you bottom out,
it's like a drop to flat, for example.
Yeah, and so yes, I think it's the load case where most of the parts of the bike are working at the same time. So with this load case, we could see a lot of area we could improve slightly. You can see some red here, some red here. So basically when it's red, we are reaching the limits of the material. So it's where we need to refine the part. So for example, here you can see a little area where it's red. So we have what we can call a stress riser, because basically in this area the material goes to zero. So in order to fix that, we simply move the wall where like the seat tube will stop, and by just moving this wall we can add a bit more material in this area, and then the problem is solved.
Okay, and here you see in this load case is red as well, but this solution is addressing the same problem, so we didn't have to make adjustments for this load case.
Yes, for the choke mount was pretty interesting because we just ran it in the simulation, but it was just a concept. The design wasn't finalized at all, but as you can see here we have some red here as well, so that means that in this area we need to add more material. But for example, in this area, you can see it's pretty blue, so the material is not working in these areas. It means that we can remove some material.
Exactly, so basically the FEM helps us to go either way. Either we want to add some material, or it shows us there's some material literally being bored and not being used, and we don't want that because we want to have ultimately a lightweight product. So it also shows us where we can shave off some weight. Do you have any other interesting points to look at? I think that part was maybe also interesting to see.
Yeah, we can have a quick look. In this part, you can see that here the parts approach its limit. So we could solve this issue just by adding a thicker wall. And it's pretty interesting that just adding few millimeters of material can add like so much stiffness.
Okay, so ultimately everything is about the correct distribution of the stress, and more material helps usually. Bigger radiuses helping usually. And what else is there to say? And so we cleared the data for Spantec, is the CNC company, just a few, like 1 hour drive from us. And they already started CNC machining the head tube. We already received the video, and I will show it to you right now. Just enjoy. Yeah, it looks pretty nice, right? We love it. We are super excited. And this afternoon we finished the drawings and sent them the drawings for the other 3 lugs. And we will receive them in January after our Christmas break. And yeah, we are super excited. And maybe we throw in a little video about all the open questions from our visit with Compotech. Yeah, I think that's pretty much it. So we wish you a Merry Christmas and a Happy New Year. See you in 2027.
27?
26.
Wow.
We
We are in
skipped one
different.
here. See you.